So it doesn't matter if it's math related or anything in the real world. Take 1 minute right now to think of as many things that exist that are opposites. Go. Pause the recording if you need more time. I'm sure a few things came to mind, right? Up and down, left and right, hot and cold, some of the basics. But you could get real creative with that. So we know what opposite means in general, but what's the word for opposite in math? You hear it all the time, and that's the theme of the day. It is inverse day. We're talking about inverse trig functions. Let's get into it. If it ever goes. There we go. Let's zoom out a bit. Okay. Our two goals determine the exact and approximate values of inverse sine and inverse cosine expressions. Okay. And explain how to restrict the domain of a trig function to make it invertible. Remember what it means to make a function invertible. It means you can find the inverse. It means it has an inverse. Okay? Which is good because you can prove things. You can undo things, right? That's why we care about that. So let's get into it. Here we go. Um, Two ways to write the inverse of sine. There they are. Okay. I'm not sure what that symbol is there. Let's get rid of that. There we go. Two ways to write the inverse of sine. You could write arc sine. Sorry, skipping ahead. There we go. Or sine of -1. Okay, that is not an exponent you're going to work out. Just know these are two different ways to say the same thing, the inverse of sine. So we're really going to focus on the inverse of sine today. There is arc sine, arc cosine, and arc tangent, but this is our strong focus. And let's get into a recap, a little refresher before we look into the inverse. So go ahead, take a moment to look at this graph. I already chopped up the unit circle to quadrant 1 to make things a little easier. Go ahead and circle sine of pi over 3. I guess circle it with your mind since we're watching this on a recording. Where is that? Well, your thought process should be first, where is pi over 3? Then we're thinking sine. We know sine is the y value related to that angle. So the answer is square root of 3 over 2. Okay? In other words, the sine of pi over 3 is square root of 3 over 2. Or you could also say the sine of 60 degrees, right? Those are both correlated here. Now, what would you say if I asked you what the degree in radian is associated with sine of pi over 3? Hmm, it's a different way of thinking, isn't it? What degree in radian? Well, it's going to be right here. Do you know what you just did? You actually just found the arc sine, aka the inverse sine. Okay, the thought process is backwards. In this situation, you're looking for the sine first, and then you're going on to look for the degree and or the radian. It depends on the question that's being asked. In this case, we're pointing out both. Not too bad, right? You just need to know where to look. So let's do a quick recap of how we thought about this. In this case, we look at the radian, then we look at the y value. But when we're going arc sine, we look at the y value, then we look at the radian. Okay? Inverse is opposite. It makes sense that you're thinking about this in reverse, right? And there it is. Step one, step two, to find arc sine. So far, so good. Now, we just found this to be true. It's all written out there. I decided to write it with the degrees instead of the radians. Take a moment to look about it and think about what moved where. Well, again, we're talking about inverses, we're talking about opposites. Everything switched places, right? The 60 degrees. I'm just going to highlight the 60 degrees. That moved from the left to the right. The square root of 3 over 2 moved from the right to the left. And of course, we need that word arc there to show that it's the inverse. So everything switches places the way we think, reverses. That is inverse. Okay? To further understand inverse and how they work with arc sine, arc cosine, arc tangent with the unit circle, we need to remind ourselves about cosine and sine and domain restrictions. So cosine goes with what and sine goes with what? Well, cosine goes with x, which is all of the possible, which is the domain. Sine, I'll just highlight all these, and then sine goes with y, which is the range. Okay? And remember, domain describes all of the possible x values on the function you see, or on a graph, the graph line you see. And the range represents all of the possible y values. And where do we see x and y values? All over the place. On a graph. This means there is graphing involved with the unit circle. Aren't you excited? Well, if you're not, don't worry. Take a deep breath, relax. And you guys already know I'm here to help you. I'm here for you, and we will never give up. All right, so we're going to go ahead and start to learn about how these connect by watching a short video. And this is important not just for this unit, but actually unit one next semester is all about this. Let's take a look. Not sure if I shared the audio. Yes, I believe I did. Here we go.
From the unit circle. In this unit circle, I can freely rotate the terminal arm about the origin to create different angles in standard position. Now, recall that the cosine of this angle here, corresponds to the x-coordinate of the point where the terminal arm intersects the circle, and the sine of this angle corresponds to the y-coordinate of the same point.
Okay, you've learned that, right? You've learned that in this class. The y value is the same as the sine, and right here he's graphing a sine function. Okay, notice the x-axis. What kind of values are those? Those are familiar, right? Those are the radians from the unit circle. It's not labeled all around this unit circle, but basically what's going to happen is he's going to show you how the sine values are graphed. It's not the x and the y, because remember, this is cosine, this is sine. So as he rotates this terminal side around, he's going to start at the initial side, as we know to do, and he's going to rotate around, and wherever the line goes, there's going to be a line being graphed over here. The x value is the distance traveled around the unit circle. Notice those distances here. And then the y value of the points that are going to be graphed is the y value here, right? The sine. So that's where these points are coming from. You're going to see it in a moment. Don't worry if it's confusing. Hopefully it all makes sense. But you're not going to ever see the unit circle with the graph sine function probably ever again in this class. It's just to show you how the two relate. So pay close attention.
So what would the graph of y equals sine x look like? What I want to do here is to create a graph of the sine of each angle versus the angle. So if you were to think about a table that we might use for this graph, in the first column, we would have different angles, say from 0 all the way to 2 pi. And in the second column, we would have their corresponding sine ratios, or in other words, y coordinates. Okay, so let's take a look at what this might look like using the unit circle. So when I have an initial angle of 0 radians, my sine of 0, look at the y coordinate, is 0. Okay, so that's where our graph would start. It would start with 0, 0. 0 radians, sine 0 equals 0. Okay, so let me animate this for a few seconds here. Okay, let me pause right there and let you know what's going on here. So what's happened here is I've started to rotate my terminal arm around the unit circle. And so the angle in standard position is increasing. And as this angle increases, so is my sine ratio. Remember, it started at 0, and it's been climbing from 0 all the way to 0.459, right? In fact, if you think of the sine ratio as the height of this right triangle, you know that the sine ratio is going to keep climbing and climbing and climbing and climbing until it reaches an all-time high of 1. So let's see that happen.
Okay, boom. Where is this? How far around the unit circle is that terminal side, that blue dashed line? Well, if all the way around is 2 pi, halfway around is 1 pi, half of that is half pi. So pi over 2, which isn't labeled there, but that's pi over 2. And then the y value, the height, is 1. Notice right now it matches with this. Now, on this graph, just think of the unit circle for a second. When you're going this way, are you going up or down on the y-axis? Up, right? So that makes sense that the y values are going up here as well. So there's a very clear correlation. Now, what do you think is going to happen to this purple line as he rotates from here to there and then from here to there? Think about it. Hopefully you can predict it. Let's see what happens.
Okay, and there it is. So it just climbs and climbs and climbs until it reaches an all-time high of 1. And now, if you were to predict what the sine ratio, what's going to happen to the sine ratio, you can see, well, A, it's going to come down. And not only is it going to come down until it hits 0, but once it hits 0, it's going to go into the negatives and keep diminishing.
Because the y values are dropping, right? We're moving downwards.
All right, so let's take a look at that happening, right? So sine ratio is decreasing, right? Because the sine of the angle is decreasing. Okay, until we hit pretty much an all-time low of -1. From there, we've only got a quarter turn of the circle left, but it's a more optimistic one, shall we say, because what's happening is we will anticipate that the sine ratio will climb out of the negatives back to 0, right? So it's at an all-time low of -1 right now, and it's going to just keep climbing and climbing and climbing, just as our pink graph is climbing and climbing and climbing until it reaches 0 again. Okay, so now if I were to allow this to continue.
So notice now we've gone around the unit circle one time. The unit circle one time. So we've traveled a distance of 2 pi. It went up, down, and back up. It started at the x-axis, it ended at the x-axis, but we already know we can travel around the unit circle more than once. So how long do you think this line will carry on?
The graph until, let's say, 4 pi. Let's just see what happens there. Okay, so as I'm rotating around again, it seems like I've heard this story before. I'm just moving around. My sine ratio increases until pi over 2 and then decreases. And this idea just repeats over and over again. Okay, so I'll pause it right there before it gets 4 pi because it resets.
So the answer is an infinite number of times. You can travel around this circle to your heart's content for days and weeks and months. No one's ever going to do that, but you could, and this will continue on forever. Now, we don't care about the infinity of it all. We care about some more specific information, like specifically domain restrictions. So let's go ahead and take a look at what those are and why we care about them. Do you remember, first of all, how to tell if this graph line is a function? Jog your memory, pause the recording. If you'd like to think about it, try it out, look it up. And then, so that's to tell if this actual line is a function. But do you also remember how to tell if the inverse of the graph line is a function? Let's see if you remember. To tell if the original graph line is a function, you're going to use the vertical line test. So if you take a vertical line, you want to ask yourself, at any point, does this vertical line touch the graph line more than once? If it doesn't, it's a function. It passes the vertical line test. So this is a pass. It is a function. But what happens when we draw a horizontal line? The horizontal line test is done the same way. It's just horizontal. We ask ourselves at any point, does this horizontal line touch the graph line more than once? Obviously, very much so, right? So this is a fail on the horizontal line test. And what does that mean, though? If it fails the horizontal line test, it means it's not invertible, right? It means it doesn't have, it means its inverse is not a function, okay? So what we want to do now is give it domain restrictions to make it invertible. But why? Why do we even care about making it invertible? Why don't we just leave it alone? Well, we care if functions have an inverse because it allows us to undo the operations performed by the function. In other words, it allows us to find the arc sine, arc cosine, and arc tangent. When you can do and undo things in math, you can prove and disprove things. So inverses are very useful and helpful. So with that said, please go ahead and circle or highlight in your mind a section of the graph that's invertible. We're going to chop it up a little bit. Where is it invertible? Okay, you may have noticed the same region I found. You may have noticed this section here or this section here. These all pass the horizontal line test, right? Specifically, the section I've decided to choose right here. The graph line never crosses the horizontal line more than once. So, we've targeted a section of the graph that's invertible, but how can we describe this section? We need to use math terms, right? We need to look at the x values and figure out how can I tell people that I just want to look at this part of the graph. This is a great skill to test yourself on. Can you write the domain restrictions? So what we want to do is we set the domain restriction from this value, negative pi over 2, to this value, positive pi over 2, because that's where we're looking, isn't it? We're looking from here to there on the x values. So this describes this section, but more often, the way you're going to see it written is like this, where it shows the x values between negative pi over 2 and positive pi over 2, also including those values, which is why we have the underline. Now, let's see if you can identify where that domain restriction is on the unit circle. We're taking this here and we're trying to identify where are those values. Remember, the initial side is here. Use that to help you. So if I'm traveling I see negative pi over 2. Well, it's easier to focus on positive values first. So if I'm traveling to positive pi over 2, I'm going to go counterclockwise and I'm going to stop there. So basically, quadrant 1. Okay? That is included in these possibilities. Okay? Now, if positive square root of 2 is right up there, then negative square root of 2 is immediately below. So travel the equal distance in the negative direction, which is clockwise. So quadrants 1 and 4 are where the domain restrictions are for arc sine. Great, you just discovered the domain restrictions for arc sine, but here are the others as well. There's arc cosine and arc tangent. You want these in your notes. Get them down now. And I have one more question for you before you go, which kind of ties this all together. Can you find the arc sine of negative square root of 2 over 2 in degrees and radians? Answer very carefully. Pause if you need to, because we're about to show what happens. Well, we pointed out for arc sine, the domain restrictions is quadrants 1 and 4. So this half of the graph, this is a no-fly zone. We are not traveling through there. Not at all. So since arc sine has those domain restrictions in quadrants 1 and 4, you can only travel within those domains. Okay? This means arc sine, any arc sine, for that matter, in quadrant 4 will be negative. Okay? We already know if we're traveling clockwise, that is the negative direction, right? So if you go positive to help you find the negative, right, you could go to positive 45 and pi over 4 and then draw a vertical line down, right, to find negative. So negative 45 degrees, or in radians, negative pi over 4 radians. Okay, don't forget that. You can't keep traveling around. If you're talking about arc sine, you need to stay in that realm. There's no quiz today. Make sure you study so you understand this, and I will see you next time.